36 says use Newton's method to find the absolute maximum value of the function so Newton's method, poor little dude. Newton's method. Well, hello. You work really well. To find absolute max this on, where'd you go? There you are. 0 to pi. So it's not saying find the roots of this. This isn't my f that I use in Newton's method. It isn't. You got to stop and think, what function do I want to attack with Newton's method? It doesn't say anything about making this 0. But of course, do the first step of doing this. What's the first step for finding the absolute max? Take the derivative. So it'll be product rule, that's 1, so I get cosine x. Derivative of cosine is minus sine. Y'all should be able to do that. That's, now what am I going to do with that? Yeah, and that's where Newton's method comes in. So this will be this is the f of x that I use in Newton's method. Here you can call it g of x because f is already something else. Or you can call this g and call it f so it fits better in Newton's. F and g are like x and y. It doesn't matter what they are. They just have to be something. You guys semi with me? So that's a problem that's kind of like you can't just start attacking what you see in the problem. You have to think about it first. This is not the function I'm attacking. This is the function I want to attack. Then you use Newton's method to figure out where that's 0. No, yes, yes, no. Again, I never want to play poker with any of you. None of you. And you're like, yeah, John, I don't want to play poker with you. Yeah, right. How would I figure out a good guess? I mean, that would be, if I'm sitting out there, I would ask that question, how the hell do I get this started and tell me anything about a guess to use? I know it's got to be between 0 and pi, so I can just pick something in the middle of that. Pi over 2. Right? I mean, so this one's got kind of like a set interval. But what do I need to really make sure to see if that makes sense? I mean, does this change signs between 0 and pi? Right? No? Yes? Okay, well, I mean, one way to figure out where there's a root is to pick a number that's between two that are on opposite sides of the x-axis. One's positive on one side, one's negative on the other side. There's a root between if it's continuous. And I know that this sucker is continuous. It's made up of trig functions and polynomial functions. It's continuous. Okay, all right. Now, on the other end of this, well, you do Newton's method to this, and you're going to get what? What are you going to get once you do Newton's method? What exactly are you going to get? The what of this function? What is doing this do? What is doing this do? Setting f prime equal to 0. We're finding the critical numbers. So to find the absolute max, you would just evaluate the function, add the critical numbers and 0 and pi, see who wins. In this case, you only want the max. So it's just a one-sided contest. You don't care about the min. Okay. Is that cool? All right, so that's the first step, is to realize what function are you actually attacking. Is you start to do this process so that you can see what you actually are working with. Did you get further than that, or does that help you?
Yeah, that's good.
Okay. Anything else from homework stuff? I mean, some of them get a little weird. Yes. Number which one? 22. Oh, okay. You gotta love it when it says, do not evaluate the limit. You're like, oh, thank God. So you just gotta set the limit up. And this is that stuff we got into last time. So first off, it says use definition 2. So you go back to definition 2 to make sure you're doing the right stuff, and then it's just what we did last time, right? Well, actually, we haven't. Yeah, I didn't realize they actually. Oh, well, 5.1 they introduced the form of this. 5.2 we actually started evaluating this. So here's the form of the area under f of x from x equal to a to b using n rectangles. So let's see if you guys remember. I'm going to use some summation notation. Actually, let me start off really, really basic. The first thing I'd figure out is what the width is for the rectangles. What would the width be? What's the... Yeah, you want to take how far I've got to go, A to B. So that's B minus A wide, divided by how many rectangles I'm going to use. That's the width. I like it. Again, this is kind of scary how much physical sense this makes. How many rectangles fit from B minus A? Well, actually, I know how many rectangles. How wide do they have to be so they fit perfect from A to B? And then what else do? So here, let me give us a little visual. Here's my f of x. All right. So once I figure out what the width is going to be, I then have to take the height of each rectangle. So it could either be this or it could be this. What I pretty much always do is I do it on this side. You'll see today I'm going to do this side. Let me ask you this. All right. So we saw last time how I could use the left endpoint or the right endpoint. And if we average those, we get a better approximation. Is that cool? Because if one overestimates, the other one will underestimate. If my function is symmetric around the region I'm dealing with, they will both be the same. Because then on one side it over and the other side it underestimates. Let me stop there. Is that decent? Okay. If I let the number of rectangles go to infinity, what happens to the width as the number of rectangles goes to infinity? What is the width approach? 0, because I'm dividing by bigger, bigger, bigger. So when I start letting the number of rectangles go to infinity, it doesn't matter what point I use to talk about what the height. In fact, if any of you guys are reading the book, they talk about like xi star. It's some random number to designate the height, because why does it not matter? Because the width is going to go to 0. How many choices are you going to have to figure out the height? None. So on the way to getting to an infinite rectangles, it doesn't matter what point you pick to figure out the height. The left end point, the right end point, the midpoint, any freaking random point in there, because I'm going to have less and less and less until I get no options. All right. And again. So what I always use, just to make the math a little bit easier to look at, I always use right end points. So how do I figure out if I use right end points, what is the area of this first rectangle? It's my f of x. Yeah. What would this be? Let me get you guys started. What would this right here, what would this be? What's that? put it all together. Where does that rectangle start? At A. How wide is each rectangle? How wide is each rectangle? Delta x. Let's consolidate all that shit with this, right? I like it. So what is that x coordinate right there specifically? Specifically. Oh, yeah, I got this. X1. No. What is it? Based on stuff we know. This rectangle starts at A. How wide is it? Delta x. So where's that? A plus delta x there. It's delta x away from where it starts. I like it. Where would the next rectangle, what would the next one be for the next rectangle? A plus 2 delta x. What about for the ith rectangle? If the first one's A plus 1 delta x and the second one's A plus 2 delta x, what about the ith rectangle? Where is it? A plus I delta x. Okay. This is a process that should feel very familiar about how to construct the general way to represent something. Okay, I like it, I like it. So, let me be a little less specific here for this first step. So if I add up, let me do this with the better pen. If I add up I equals 1 to n, all the function values, that's the height, times the widths. If I add up every height times the width for all the rectangles, all n rectangles, what will that give me? Not a number. What's the idea? What does that give me? If I add up every area of every rectangle I can create doing this process, it gives me a feel for what? Area under the curve from A to B. I like it, right? So this right here is approximately the area from A to B under that curve. So this is, the smaller n is, the weaker the resolution. Is everybody cool with me saying that? Because if I increase n, I get more rectangles, sort of like getting more pixels. So you get higher resolution, right? So how do I make this not approximately, but perfectly equal to? Same thing we've been talking about for a while. I let n go to the opposite. Yeah. So if I take the limit as the number of rectangles goes to infinity of this, that will equal the area in there from A to B. So if you look at definition 2, this is basically what they have written. So all you have to do now is take the function they give you in the problem, take that function, put xi in it, and then multiply it by the width. So let's see, what's that function they give you? This is number, what was it, 22? Or was it the other one? 22, yeah. So here's the function they give us. It's number 22. Bless you. Actually, I'll tell you what. Let me do 21. I'll do 21 all the way. So I don't do your homework for you, but I give you a complete feel for this. So here's 21. You guys got to do 22, I guess. From 1 to 3. So the question for 22 is, for 21 too, is set up this to find the area under this function from 1 to 3. So you've got this form. This is what definition 22 gives you. Definition 2. So what's f of x? It's that. What's delta x? Somebody help me with what's delta x for this problem? What's delta x? What is delta x always? This. So what's delta x for this guy? What's b? So it's 2 over n. So it's the width across which I'm interested in divided by how many rectangles I'm using. If you catch yourself saying, well, they didn't tell me how many rectangles. No, they didn't, so I just put n, because I don't know. And I know the point of this problem is to let that go to infinity. So I need to represent it by n, because it's going to infinity. What is f of xi? Because that's what else I need here, right? So this, you see, all I'm doing is I'm taking the form they want me to work with, figuring out each piece, using what they told me, and plug that stuff in. And then I stop, because they said don't worry about figuring out the limit yet. That's what we're going to do in the next section, is actually figure out what the limit is. So what's f of xi? It's 2xi over xi squared plus 1. I don't think they want you, I could get, well, what the hell? Let me get more specific. I don't think they want you to yet, but we're going to have to anyway. Let's see if you guys can remember. So here's a picture, I don't know what this looks like, blah, blah, blah. So I want to go from 1 to 3. What is xi? So let me ask, let's build it up again. Same thing we just did a minute ago. What's x1 going to be? That's this side of the first rectangle. What's x1 going to be? Same reasoning we just used a second ago. Where does that rectangle start? Where does that rectangle start? 1. That's where we're starting. How far away is it to the other side of the rectangle? Yeah, so this will be x1 is 1 plus 2 over n. What would x2 be? x2, I would just add another 2 over n, and then I just keep adding 2 over n. So what's xi? It's going to be 1 plus 2i over n. I just add I 2 over n's. 2 over n is how much of a step I take to get from one side of the rectangle to the other. That's how wide it is. So how do I get to the ith one? Start at 1 and take I steps. So if this one is going to be 1 plus 1 step, what's the next one going to be? 1 plus 2 of these 2 over n's. I'm going to add another 2 over n. So to get to the ith one, I have to add I 2 over n's to get there. So for this problem, let's put this all together. Let's see, do I have all my pieces? I have delta x, check. I have f of xi, I will in a minute, because now I know what xi is. So what is f of xi? It's going to be twice that. Twice xi divided by xi squared plus 1. Okay, stop. So if you take this in stages, what does this need, f of xi? Well, f of xi is just freaking twice xi over xi squared plus 1. That's what f of xi is. I just plug an xi in. If I can then figure out what xi is, I can make that a little more specific. So then I just put in what xi is. And now I can put, and again, this is construction approach to this problem. Do I have this? Yes. Do I have this? Yes. All right, good. I got everything. Limit n goes to infinity. Sum I equals 1 to n. F of xi is right here. times delta x, which is this. Does that look easy? Not necessarily, but it's because it's a big problem with a lot of parts. So what do? You attack each part separate. Then you put them all together. Now the part of this has got me a little worried. Let me ask you this. If I, let's say there's this big, like a meter stick, but like 10 meter stick, right? You guys with me? It's like there's like this really long, and I start at, so here's 0, but I start at 1. And I mean, this thing is long. This is infinitely long. This is insane. I'm like, what the shit? Who put this here? So I start at position 1. I can see there's a 1 right there. I'm at position 1. And every step I take is 2. So if I take one step, where do I end up? If I take one step, I end up at position. Every step I take is too big. I start at 1. Take one step, I end up at 3. Okay. It's okay that it's easy. Just say it. Make me feel better. How many steps? Well, let me say this. Which way do I want to say this? Oh. If I took 80 steps, where would I end up? If I took 80 steps along this thing, I'm like, is this infinitely long? Let me start to walk along it and see if it has an end. And I keep walking 3, 5, 7, 9. I keep taking steps of 2. If you take 80 steps, where do I end up? Yeah. You end up at 1 plus 80 steps. So what if I take, it's 161. What if I take, how do I say this? Take, trying to make it relate back to you. Let's say, yeah, take I steps. What if I take I steps? Where do I end up? Yeah, 1 plus 2I, right? Because here, if I would have said take 70 steps, you would have done 1 plus twice 70. 60 steps, 1 plus twice 60. I steps, 1 plus twice I. So if this would have actually been 2 over n, if this would have actually been 2 over n, that's how big each step is. And n is kind of like a measure of how I'm feeling. Feeling all right? N is small. Feeling kind of bad? N is big. Oh, God. Got to take smaller steps. Then where would I be? After 80 steps, where would I be? I'd be at 1 plus 80 times 2 over n. After I steps, I would be at 1 plus I times 2 over n. So that's where the 1 plus 2I over n came from. I steps start at 1. I'm going to end up there. Okay. So that problem, this is number 21, I know, but 22 works exactly the same way. You would just stop there. It says don't evaluate that limit. We actually couldn't even do that limit after today's discussion. We will be able to do many, but not that one. So it's good they didn't ask you to do it. Okay, maybe. So whenever you get a problem, I really, there's parts to it, you plug them in, you get this, but what is the idea behind this? You do this before I pray. What's the idea? What is this trying to do? This, for any value of I, what does that represent? for any value of I, what does that mean physically? And I know you guys are out there, what the shit does he want from me? What do I build this whole thing off of? Take a function, and what do I cut it up into? What do I cut the function up into? I cut it into rectangles. Cut it up into strips, right? So what does this represent for any of those? It represents the area of that rectangle. So if I add those up, I get an approximation for the total area, but if I let the number of rectangles go to infinity, that's perfect resolution. It's going to stop right at the function. It's not going to over or underestimate. It's going to be perfect. And thank God we know how to handle these, so maybe we can actually do it without having to have truly infinite number of rectangles. Holy shit. We could just do that, evaluate the limit directly. Okay. So perfect segue. Let's see, any other questions from the homework? Okay. Okay. So that cool as that basic is how 22 works. So let's do this. Let's do a smaller concrete problem before we step into infinite rectangles. Let's remember how this works. Let's take a function that's not a down parabola. That's getting kind of old. Oh, let's do this. Yeah, okay. What you got, Jeff? Yeah, okay. Yeah. Yeah, just to be a jackass, we'll do that. I like it. And here's something really interesting that some teachers have a big problem with. Are you cool at this point, going back a step, going back to, bless you, something from earlier this semester? Are you all cool with the fact that velocity is negative sometimes? Doesn't mean somebody's going into a black hole. Doesn't mean somebody's like inverted, right? It just means I'm going the other way. Area can totally be negative. Same way that velocity can be negative. What is it about this function? Can anyone help me graph this? What is this function's x-intercept? What's the x-intercept? You guys don't want to play with me at all. All right, so the x-intercept is 2. All right, going from 0 to 4. What's the y-intercept? No. How do you find the y-intercept? You let... Don't overthink it. How do you find any intercept for any letter? You let all the other letters be 0. So what's the y-intercept? 8. Okay. So there's that. There's that. Maybe we know the general shape of this thing, maybe? What's a cube normally look like? Can you draw it in front of you? What's a cube normally look like? Yeah, I love you guys. Just do it. Just draw a cube. Just do it. I want somebody to go like this. Make a little x cube. All right, so a cube, from your perspective, looks like this, right? A colleague of mine calls it the giraffe graph. But I always say, well, it's missing its front leg. It's about to fall over. That's horrible. So when he cut its front leg off and want blood coming out here. But, you know, I mean, here's the giraffe graph. Do you see that? But it's about to fall over. That's so sad. Sorry. So this, come on now. This is going to be a reflection of that. And instead of going through 0, it goes through 2. So instead of going like this, it goes like this. Right? Now, where is it at 4? Let me make this a little better. At 4, where is it? Try to keep my horrible scale. probably there. 2 minus 4 is negative 2 cubed is negative 8. So it's over here. Boom. So I want you to realize ahead of time what this answer is going to be, or at least close to, considering now I might have some over or underestimate. The area I'm trying to find is the area between the function and 0. So it's this area over here. Over here, it's going to be this area. Now, my rough sketch kind of sucks, but aren't those areas going to be equal but opposite? One's positive, one's negative. What does negative area mean? All right. Why can a derivative be negative? Why can a derivative be negative? What would that mean? So if I have like the amount of water, and I find a derivative, it could be the amount of water going past me at a certain time. So if it's flowing this way, positive. If it's flowing that way, negative. So derivative can be negative to indicate direction of movement. If I have water flowing into a container, the antiderivative of that flow would be how much water there is in that container after a certain amount of time. That's what we're getting towards, but we can already kind of reason that out. If I let water flow, there's a derivative. If I take the antiderivative, it should be how much water ends up in that thing. And that's going to be positive because it's filling up. If instead I have a full one and somebody cuts a hole in the bottom of it, right? That's going to be negative. Maybe. Or even better, here's an even better one. If I have a derivative meaning flow of cash per month, right? If it's positive, that means I'm accumulating cash. The area would be positive because the area would represent total amount of cash. What would it mean if the area is negative? That means overall overall I lost money. That's all it means. So area being negative just indicates, did you overall gain something or did you overall lose something? If area is a geometrical thing, you can't have a negative area of a triangle. That's freaky. But we now realize in calculus, area is a little more general. Area can be negative the same way that velocity can be negative. All right. Let's just try this sucker out. So I'm not letting it go to infinity yet. Right? I should have picked one that would have been easier to use later, but oh well, too bad. From x equals 0 to x equals 4, using 6 rectangles, what's the first thing I need to figure out? Delta x. I need to know the width. What's the width going to be? 2/3, yeah. So 4 minus 0 over 6, 2/3. I like it. Let me go ahead and use right endpoints. Just because. So let's just draw this first rectangle. Where is the first x I'm going to use? I'm starting at 0. Big easy step. 2/3. So this first rectangle is going to be at 2/3. What is my scale? Okay. So it's going to be about this tall. So the area of that rectangle would just be the width times the height. And what's the height for every rectangle going to be? No, the width is going to be delta x. What's the height for everything going to be? The height will always be what? The height will be this function value, right? F evaluated at that. Don't make too much out of this. It really isn't. So the width tells me where to go. How tall is this sucker going to be is the function evaluated there, of course. That's the height is going to be where it goes. So that's why it makes sense that I take f of x times delta x. Because each one of those is an area of each rectangle. If I add them all up, I get the total area estimate. So for the first rectangle, it's going to be 2/3 times f of 2/3. That's the first rectangle. What's the second rectangle going to look like? Where am I at now? My input. One more step gets me where? 4/3. Okay. So now it's going to be the width times the height. Now how many more terms like this am I going to have? A total of 6, so 4 more terms. I like it. So let me just make this a little easier to look at right now. You guys realize this is what we did last time. I can factor a 2/3 out and just focus on this. Add 2/3, it's 6/3 is 2. Add 2/3, I get 8/3. Add 2/3, I get 10/3. Add 2/3, I get 4. As 1, 2, 3, 4, 5, 6. Yay! Right, we talked about that last time. Kind of as you're doing the problem, make sure you don't have too many or too few rectangles. Because it's really easy just to get in the flow of what I was just doing and just kind of go too far or stop too early. And now it's just a bunch of calculations. I showed you a shortcut with the table on the calculator the other day. Yes, I did. Yeah, I can show it to you again. I'll move this on anyway. I love how they have multiple brands in here. Now, that's not a ton of calculations, but let me just show you in case you have to use like 8 or 12 or something rectangles. It'd be nice to have a quicker way to do this. Now, let me show you, all right, I'm just going to show you the ultimate shortcut for this. Oh, there it went. Okay. Again, do you really need the shortcut? No. If you don't understand it and you want to know it, you can always come see me. And if you don't understand it, you don't want to know, you don't need it. You can just calculate all those directly. So this is really cool. Last time we did in the table, I want to show you another option. I don't know if you even know about this. If you hit Stat, Edit, you have these tables. Let me clear this out of there. If you look at the thing, yeah, there you go, buddy. Okay, so watch what I can do. So what do I want in here? I want 2/3, 4/3. I'm going to put all my inputs in here. 8/3. 10/3, and 4. Not too much glare. There we go. All right. Okay. Is that cool? That's all my inputs. I got 1, 2, 3, 4, 5, 6. Okay, cool. I don't know if you guys. And again, if you don't like this, never use it. But once I show you this, if you've never seen these work, if you've taken statistics, you must have seen this. If you haven't, you might never have seen these, right? Watch what I can do. Go to L2, and I can define L2. This is sort of like Excel, where you can define a whole column to be something. So I can say I want L2 to be 2 minus L1. L1 is above 1. 2 minus L1 cubed. Bam. Right. So there's all my function values. You guys with me? Now, this gets a little bit trippy. If I go second quit, do you see how it says list right above stat? Go to list, and then I want to do some math. I want to add up. I want to sum up L2. So that's the sum of all those function values. So the table gives you the function values, and then you still have to kind of add them up. If you want to use this one instead, these tables, then you can actually have it add them up all together for you, right? So then I get 2/3 times, what was it, -8, right? -16/3. Now, let me see if you guys, all right. If I do left endpoints instead, what is the only difference between what I've done and what left inputs needs? What would have been the first input if I used left endpoints? 0. And would it have made it all the way up to 4? No. Because the last rectangle would have been based on this height, right? I should have run out. So if I want to use left endpoints instead, I do all the same work except right here, I do f of 0 instead. F of 4 is -8, which is what this came out to be. F of 0 is 8. Guys, this is up to you. This is all shortcut shit. If you don't want a shortcut for anything, you can just redo the whole problem again for left endpoints. But all I need to do is take this side and replace it with that side. So instead of minusing 8, I add 8. Think about it. If all this came out to be -8 and I replace that with +8, it's all going to come out to be +8 now. So then from the left endpoint, I get 2/3 times 8. I get 16/3. What do I get when I average these together? What do I get when I average these together? 0. They cancel out. And that matches with what we expected. I expect this area to cancel with that area. That area is positive, that area is negative, it's symmetric. Those areas should cancel. Why did the left and right endpoints not come out to 0? Because one way underestimated, the other way overestimated, as they always do. Yes?
All your previous examples, plus the examples you have graphs are usually in the first quadrant.
I know, exactly. I know.
Easier to figure out the area.
No.
This,
No.
no, to at least visually draw it. This one is confusing me. Why can't we pick other locations under or above the graph to visualize how we can measure the area?
So,
for example, from 0 to 2, let's say, that is in the negative.
well, from 2 to 4, it's in the negative, sure.
Why wouldn't we also color the area from 0 to 2?
It is. I don't understand.
Below.
No.
Why not?
Because when we first start, you're right. We try to do things in the first quadrant to kind of make it easier to understand the idea. So what is an integral really? What does this area really represent? The area between the function and the x-axis. That's what it means. So if it's in the first quadrant, I can just say the area under the function to the ground, to the x-axis. So why is this negative? Because under is actually over.
So our goal is to always get to the
Between the x-axis and the function itself. So if this was a profit curve, if this was a, let's say, a rate of change of profit, this would have been me making money, and then this would have been losing that same money. That's what that would physically mean. Okay. So yeah, it's the area between the function and the x-axis. And you're right. It's I didn't need to say that when we started this procedure, because if I only look in the first quadrant, I could just say under the function. But it's always between the function and the x-axis. Otherwise, there would be, the minute it dipped below here, if you did the area below, it would just go forever. It would be infinite, all the time, forever. So the minute your company went here, you have infinite money loss. Thankfully, we don't do that. All right, so let's do this. So I'm going to take this procedure and I'm going to basically do the same thing we're doing, but what we always do in mathematics. especially now that I want n to go to infinity, I'm not going to have a number for n. It's going to be n. So I have to be able to work with that. I'm also not going to have a number for xi. Because xi depends on how wide it is, and if I don't know how wide it is, I don't know what xi is. So I'm going to have to work with these variables. Put that up there. Where's my lower? All right. So let's do it. Let's start with just like we did with derivatives, when we kind of tried to implement a shortcut. We started with the easiest example, and then hope to God there would be rules so that we can build more difficult functions derivatives. That's exactly what we did. So start with a really nice, really nice function. In fact, let's start with like a supremely nice function. Let's do 4 minus x. From 0 to, I don't want to, sure, why not? Just to make it really, really crazy nice. 0 to 4. Take a minute and sketch that region for me and try to determine the area geometrically. Just get the area of that based on the shape you make. This beautiful triangle. So what's the area of that triangle?
60.
So 1/2 the base times the height is 8. It's very cool. So if I use a process that's supposed to find the area between the curve, the function, and the x-axis, it better frickin' come out to 8, or maybe I can throw it all out. We forget about the second half of the class, but don't get too excited. It's not going to happen. So we're cool with that so far. So there will be some problems in the homework that just say graph this, or they give you a graph, they say find the damn area directly. Right? If all we're doing is finding areas, I really don't need calculus's help if the shape is something I know the area for. But calculus has to agree with this, or else it's not really doing its job. Okay. So what I want to do now is, that's the nice little graph, and I already kind of know the answer ahead of time, but I want to use infinite rectangles. If you've got, I gave you guys this guy. It pretty much gives the steps that we're going to use. This is the same steps I used earlier to do that one problem where I was talking about stepping around and I times the width and all that kind of stuff. So no matter if you're going to use infinite rectangles or 3 rectangles, the first step is the width. It's kind of like what gets everything going. So what would the width be here? What's the width? 4 over n. I like it. So if I was using 4 rectangles, then it would be a width of 1. That would fit in perfectly, so forth. Now I can figure out what xi is. In this case, what's A? Where does this all start? So you can see it's going to be a little bit worse if A isn't 0, but for the problem I gave you, A is 0. So it's 0 plus each step I take. So if I take I steps, xi is 4i over n. That's going to be, how to figure out the height, it's going to be this side of the first rectangle, which would be 4 over n. The next rectangle, the height would be at 8 over n. I would take another step, and so forth, and so forth, and so forth. Like it. And then I need to find f of xi. So what is f of xi? Let's do it in 2 steps. F of xi is just 4 minus xi. That's amazing. But I know what xi is. So f of xi is 4 minus 4i over n. Now I can put all this together in that form we were using earlier. So f of xi we just figured out is 4 minus 4i over n. Delta x we figured out is 4 over n. Let me ask you an interesting question, and then I'll remind you of something we came up with yesterday. Actually, I'll remind you when it comes up. Let me ask you this question. In terms of the summation symbol for this guy, in terms of the summation symbol, what is the variable? What is the thing that's changing for this guy? What's he say to do? How would I kind of start to write the terms out? What does he say to do? Let I be 1, and then what happens for the next term? I would let what be what? I would let I be 2, then I would let I be 3. And what is n in terms of the